Hi friends, today we'll see what is the RH criterion. Okay, so what is the stability analysis system? Now, so whenever we consider control system or any system here, we we go for the stability analysis using RH table or using plots. Okay. Now, here these plots we have body plots, Nyquist plot, and polar plots. Okay. We'll see about the plots later. First, we'll concentrate on RH table. Okay. Here, I wanted you to know the stability analysis system consists of 50% weightage, has 50% weightage in GATE exam. In GATE exam, I can say more than 50% also. So generally, what happens is, from the control system, the weightage is 11 to 13 marks. Okay. So if we concentrate on the stability analysis of the system, we get 5 to 6 marks easily. Okay. Other 5 to 6 marks, they depend on time response of the system, that will do later. Okay. So first thing is that easiest and simple thing in the control system is RH criterion topic, that comes under stability analysis of the system. Now we'll get into the topic directly. I don't want to waste the time on this, on the introduction. Okay. Now first thing, so for any system we have this here. That's it one. This is output y of s. Say this is input x of s. Okay. This is my system. Now here, what is g of s? G of s is open loop transfer function. What is this one? This is a unity feedback system. Okay, that means my h of s is 1. The feedback element is 1. Okay. So if suppose I have a feedback element h of s. Okay. If I write the closed loop transfer function for this, what will be the closed loop transfer function is? Consider this closed loop transfer function. Consider the denominator of the closed loop transfer function. Why? The denominator of the closed loop transfer function gives me the poles of the system. Okay. For identifying the stability of any system, I need those poles. Okay. So what I do is, I consider this part 1 plus g of s into h of s. This is called characteristic equation. This is called characteristic equation. Okay. So 1 plus g of s into h of s equal to 0. It is called characteristic equation. Okay. Now, for applying the authorized criterion on this system, first what you need to do is, if they have given you the open loop transfer function, then you open loop transfer function should be converted to closed loop transfer function. Take 1 plus g of s h of s from the denominator equal to 0. Okay. Now after doing that, after doing this, what we get is the equations which we get after g of s into h of s is of this kind, a polynomial. To so on a naught s power 0. Okay. Equal to 0. So this is the equation we get after applying the 1 plus g of s into h of s equal to 0. Now from this, we will write the table called Rautharis table. How does that look, please? Okay. What is the highest power? Suppose here, if I consider, what is the highest power? Highest power is S power n. So S power n. Next highest power S power n minus 1. Like that, so on up to S power 0. Yep. These are the S terms. Now I want to write the coefficient terms in the Rautaris table. Okay, what is the coefficient of S power n? Is 0. What should be the likewise I want to write for every n term. That means if my n is starting is S power 4, that means I need to write some constant k here. I need to write the odd even terms at once and odd terms at the once. Okay. So if I consider this, then I need to write all even terms first or odd terms first, depending upon the n value. Okay. Here, suppose I consider n is 5. Suppose this will be 3. Next highest power is 3. Or else suppose n is 3, this will be 1. Okay, all odd terms at once. Now next all even terms at once. A1, A3, the next term. Okay. For the next power, if it is not there, for the next power, how will I get that thing? Is that multiply A1, A2 minus A0, A3 by A1. What are the next terms? 0, 0. Similarly, this column and this column. That gives me same. Okay. So after doing this comes under the first column of Rautaris table. Okay. Now the values which are on the first column of the Rautaris table define the stability of the system. Okay. That means okay. Now here, whatever values I have in the first column of Rautaris table, that define my stability of the system. Okay. Suppose here I have the coefficients. Let's say A0, A1, A2, A3 up to so on. I'll take a finite system. Okay, for easy understanding. Let's say this is my system. Okay, so here whatever coefficients I have on the first column of the Rautaris table, if there is no change sign, okay, that means here to here there is no sign change, here to here there is no sign change, here to here no sign change, here to here no sign change. If there is no sign change, then the system is said to be stable. The system is said to be stable. Okay. Suppose if there is any sign change, then system is unstable. If the system is then unstable. Okay. So these all we'll be doing under the S plane. Okay. Now in the S plane, what happens is this is right hand side of S plane. This is left hand side of S plane. Right? Now, what does this now? Suppose if there is a sign change in the system, then number of sign changes. What does this indicate? What does this number of sign changes indicate? In the first column is number of poles on right hand side of S plane. Okay, number of sign changes indicate that number of poles on the right hand side of the S plane. If there are 4 sign changes, then there is 4 poles on the right hand side. Okay, so whenever we consider the S plane, what else we know about the S plane is, when the poles are on the left hand side of the S plane, the system is said to be stable. Okay, suppose here are my poles, then I can say my system is stable. There are no poles at right hand side, then it is said to be stable system. Okay, whenever I have at least one pole on the right hand side, then the system is said to be unstable. Okay, or else I have only 2 poles, that means one is on the left hand side, one is on the right hand side, the system is said to be symmetrical, unstable. The poles are said to be symmetrical about the origin. Okay, we'll see what are different types of poles existing on the right S plane later, but for now, for the basic part, consider the system. If any sign change occurs in the first column of the order is stable, then it is said to be unstable system. If there is no sign change, then it is said to be stable system. Okay, this you keep it in mind. Okay, just with a small example, I conclude this video today, and we'll go for the other example now. What is this? This is for the this is a trick for the gate. Okay, suppose given C is the characteristic equation. Okay, suppose they given this is the characteristic equation they given. Okay, whenever there is a characteristic equation and mainly it is of order 3. Okay, whenever you see these kind of problems, simply what you will do is multiply the power 2 and power 1 terms and multiply these last 2 terms. Okay, the coefficients. What you get, the coefficients you get is, here it is 6 into 3, 18. There is 10 into 1. 8 is greater than 10. Whenever the inner multiplication, I will say this inner multiplication, this outer multiplication. Okay, whenever this inner multiplication is greater than outer multiplication, then the system is said to be stable. If you can check. Okay, system is stable system. The system is stable system. Okay, if you want, you can check by applying Rhodri's criteria. I'll explain the Rhodri's criteria in the next video for this same equation. Don't worry. Okay. Next, if suppose for same type of problem, now see, what is the multiplication here? The same order. Inner multiplication is 32. Outer multiplication is 32. Inner multiplication equals outer multiplication. This type of systems is called marginally stable systems. Marginally stable systems. Sir, where we find this kind of tricks used in the gate exam? If you will ask, they'll give you, whenever this is not the conditionally stability system, but after this we'll go for conditionally stable system. Then when we have those kind of problems, this gain, whatever this gain, this is called the DC gain. This gain won't be there. There will be some sort of values they will be giving, like k by 8 or something or the other. Okay, because that depends on the condition k. So then they'll ask, if the system is marginally stable, find the value of k. Then you need not go for the Rhodri's criterion and do all the process for obtaining the value of k. Simply you can multiply the outer parts and multiply the inner parts, you get them, you get the k value. Okay, there you use this kind of system. And they'll give the equation in third order. If they ask for the stability, you can tell within 10 seconds by multiplying inner multiplication or outer multiplication. Okay, so that's all for this video. The introduction for the intersection for the RS criterion and how to generate the characteristic equation and some trick for the gate. In the next video, we'll solve a problem related to Rauthat's criterion. That's all for this video. Thank you.